In this video, we discuss how to treat Lorentz forces in quantum mechanics. We start with understanding minimal coupling, and then we move to fields and gauge transformations, and then invariance under gauge transformation of the Hamiltonian, and finally, we talk about the Coulomb and Lorenz gauges. So, in quantum mechanics, we don't deal with forces. And the classical interaction of the Lorentz force, that is, the charged particle with electromagnetic fields, cannot be described in the form of a potential gradient, which is the only way we can treat forces, so-called forces, in quantum mechanics. So in order to deal with this kind of interaction, we have to reformulate the Hamiltonian to account for electromagnetic fields. So basically, we don't treat this as a potential, but we have to rewrite the Hamiltonian, part of the other parts of the Hamiltonian, to include the forces in the form of potentials. So, the good thing is we can use classical electrodynamics to help. If you look at the classical Hamiltonian for a particle in the presence of an electromagnetic field, it's written as 1 over 2m times the quantity p minus q times a, quantity squared, plus q phi, where a is the vector potential and phi is the scalar potential. And the electromagnetic fields are derived from the scalar and vector potentials, such that E is equal to minus the gradient of phi minus the time derivative of A, and B, the magnetic field, is equal to the curl of A. Now, we can use this Hamiltonian, convert it using operators, using the momentum operator, and get a quantum mechanical Hamiltonian that we can apply to the use of these interactions with electromagnetic fields. And that becomes the Hamiltonian, quantum mechanical Hamiltonian is 1 over 2m times minus I h bar gradient minus q times vector potential quantity squared plus q times the scalar potential. And these are operators that are then applied to the wave function of interest. And therefore, the time-dependent Schrödinger equation becomes I h bar partial psi of r and t dt is equal to 1 over 2m minus I h bar gradient minus q a quantity squared plus q phi applied to psi. Now, these potentials in classical electrodynamics are not measurable, but they're used to describe the fields which are. So that, as we wrote before, the field is something that's measurable. The potentials are not measurable. Similarly with the magnetic field is measurable. The potentials that we use for classical electrodynamics are not measurable. And the potentials can arbitrarily be changed via gauge transformation, which we'll talk about more in detail later, without altering resulting fields. And the gauge transformation typically looks like phi being replaced with phi prime is equal to phi minus the time derivative of the gauge transformation lambda. And A, with that same gauge transformation, you have A goes to A prime, which is A plus the gradient of the gauge transformation. Now, in classical electrodynamics, the fields are what count. The potentials can't be measured. In quantum mechanics, however, the potentials are exactly what we need to have. And they're an integral part of the Hamiltonian, while the fields are not really in the picture at all. So the Hamiltonian, as we wrote before, was 1 over 2m h bar over I gradient minus q times a quantity squared plus q phi. So you see what we've done here is we've replaced the momentum, the kinetic energy term, which was simply this first term, we've added the effect of the vector potential in here into this term, and we sort of mixed it all together. And then, of course, we have the scalar potential, which acts like a potential. So, the Hamiltonian itself is also invariant under gauge transformations, as it turns out. So not only are the fields invariant in classical mechanics, but the Hamiltonian in quantum mechanics is also invariant. So in classical physics, we don't expect to see an effect on a charged particle unless your field is non-zero. However, in quantum mechanics, this is not necessarily the case. The vector potential can affect quantum behavior, even though the field is zero. So you can imagine that there is a field which is zero because the vector potential has no curl. But the vector potential still folds into the Hamiltonian and will affect the wave function and the eigenvalues and eigenfunctions. And so we're going to see how this works. We'll start by looking at the invariance. We want to understand how the electric and magnetic fields can be invariant under the gauge transformation, and then how the Hamiltonian can be invariant under the gauge transformation. So we'll start with the electric and magnetic fields. And the gauge transformations are here. This lambda is the gauge transformation, and you have the replacement of phi with phi prime and a with a prime. So we'll start with the electric field. E is now going to be minus the gradient of phi prime minus the time derivative of a prime. So we're going to assume that we have the same form, but now we've replaced the gauge transformed potentials. And we want to see if the electric field remains the same. Well, the first thing we want to do is substitute in the phi. So if we substitute in the phi here, and then we substitute in a prime as well, we get for the first term, the gradient of phi prime gives you the minus the gradient of phi prime gives you minus the gradient of phi, and then plus the gradient of the time derivative of the gauge transformation. From the second term, which is the minus the time derivative of a prime, we get minus the time derivative of a minus the time derivative of the gradient of the gauge transformation. Now, because the time and spatial derivatives don't really talk to each other, we can interchange them without any penalty, and you can see that these two terms will then cancel. And so we're left with minus the gradient of phi minus the time derivative of the vector potential A, and that's exactly the field. So the electric field, when you make a gauge transformation of this kind, does not change. The magnetic field, similarly, can be seen not to change as well. So we have the curl of A prime. So that means we're going to take the curl of these two components. That gives us the curl of A plus the curl of the gradient of the gauge transformation. But the curl of the gradient is simply equal to 0 by definition. And so this gives us then the curl of A, which again goes back to the original potential, the original magnetic field. So we can also show that the solution to the Schrödinger equation is also invariant under gauge transformation with the addition of a phase factor. And we can show that the Schrödinger equation, written like this, where instead of psi and a and phi, we replace it with all the gauge transformed terms. That is, we replace it with psi prime, a prime, and phi prime. This also holds when the Schrödinger equation with everything unprimed also holds as well. And the only change we have to make is we have to replace the original wave function psi with psi prime, which is psi times a phase constant, a phase factor And the phase factor is e to the I q lambda, which is a gauge transformation, divided by h bar. So we treat q lambda as sort of an energy. This becomes a phase factor. It becomes dimensionless. All right, in order to do this, we have to first find out what the initial term in the Hamiltonian, h bar over I, gradient minus q times a prime applied to psi prime, will give us. Well, we're going to substitute in for our expected value of psi prime, and we're going to substitute in for a prime as well. So remember, a prime is a plus the gradient of lambda. And so this then becomes h bar over I gradient minus qa minus q gradient lambda times, all applied to e to the I q lambda over h bar times psi. Well, if we take this term here, we're taking the gradient of the first term, the exponential. That gives us q times I divided by h bar, so the h bar and I cancel. We get q times the gradient of what's up here, which is the lambda. So we get q times the gradient of lambda times e to the I q lambda over h bar lambda, psi. And then we have to take the term where we take the gradient of the second part, which means that we have h bar over I e to the I q lambda over h bar and times the gradient of psi. So that comes from the first term. The second term gives us minus q a times e to the I q lambda over h bar psi. And the third term gives us minus q gradient of lambda e to the I q lambda over h bar psi. So we have four terms to deal with. The first and the last term are exactly the same, and they cancel because of the minus sign. We're left then with two terms. H bar over I e to the I q lambda over h bar gradient of psi minus qa e to the I q lambda over h bar psi. So that's this term applied to psi prime. We now want to apply it again because that's what's in the Hamiltonian, this term squared. And so we've got to apply it again, and we got to apply it to the result of our first calculation, which is this, and we ported that over here. And we're going to apply the same terms here, where we replace the a prime by a plus the gradient of lambda. And so we get these three terms applied to this result from the first time we applied the same thing to psi prime. So now we're going to do the same thing here. We have to apply it to this term and to this term. Then we have to apply, multiply this and multiply that. And then here we have to apply the gradient again to both terms. So the first term, that is the h bar over I times the gradient applied to this term, gives us two terms. One is when we apply it to the e to the I q lambda over h bar, we're going to get a gradient of lambda dotted into the gradient of psi. And then we get a I q h bar out from the top. And we get I q lambda 8 over h bar psi. And then we have the second term, which is where we just apply this to the gradient of psi, and that gives us the Laplacian of psi, del squared. And then the i's cancel, give you a minus sign, the h bars become h bar squared, and you have h bar squared e to the I q lambda over h bar times the Laplacian of psi. So that's this applied to the first term. Now we've got to apply it to the second term. Well, That gives us, first of all, when we apply the gradient here, we're going to get minus h bar q over I del dot A, because these are both vectors, so the dot product. And then you have e to the iq lambda over h bar psi. The second term over here gives you minus q squared, because you pull down the second term here. When you take the gradient of this term, you get an iq over h bar pulled down. That cancels the I, cancels the h bar from here, and gives you a q squared. And then you have A dotted into the gradient of lambda, e to the iq lambda over h bar psi. Then you have a third term when you take the gradient of the psi, and you get minus qh bar over I, e to the iq lambda over h bar, A dotted into the gradient of psi. And then you have four terms from these two multiplied times these two. The first term gives you minus qh bar over I, e to the iq lambda over h bar, A dot gradient psi. Then you get plus q squared a squared e to the iq lambda over h bar psi. And finally, you get minus qh bar over I, e to the iq lambda over h bar, gradient of lambda dotted into gradient of psi, plus q squared a dotted into the gradient of lambda, e to the iq lambda h bar psi. So we've now got all the terms. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. Again, we can find some cancellations, because this term and this term are identical and they cancel. This term, the first term, and the penultimate term also are identical and they cancel. And we're left then pulling out the common term, which is e to the iq lambda over h bar. We get minus h bar squared Laplacian of psi plus iqh bar del dot A psi. Then we have 2i qh bar A dot the gradient of psi plus q squared a squared psi. And that's what we're after. So that's one term in the Schrödinger equation. Now, if you look at this, this is exactly the same terms that you get in the untransformed Schrödinger equation, right? And let's show that. So let's take this term applied to psi without transformation. We get h bar over I del psi minus qa psi. Then we take and apply it again to the same terms. We get h bar over I applied to this, and then we have minus qa times this and this. And when we do that, we get minus h bar squared del squared psi. That's for the first term. Then we get a second term, which is minus h bar over iq del dot A psi. That's when we apply to here. Then we get a third term, which is minus 2 h bar over iq A dot del psi. And we're combining this applied to psi with this times this term here. It gives us 2. And then finally, we have this term applied to this, which gives us plus q squared a squared psi. And so this term here with the gauge transform A and the gauge transform wave function gives you exactly the same result as when you have the original untransformed psi, untransformed A. All these terms match up exactly. Because of that, we can then write that h bar over I del minus q a prime quantity squared applied to psi prime is equal to the same term without the primes times e to the I q lambda over h bar. We can now recast the Schrödinger equation using this transformation. We've now figured out what this gives you. And now we have to apply it over on this side. So you have IH bar d psi dt, but its gauge transform psi prime gives you an additional term, which is minus q partial of lambda with respect to t applied to psi times e to the I q lambda over h bar. And that is equal to, then, this has no time dependence, I guess. So then you have e to the I q lambda over h bar times the quantity 1 over 2m, and then we have h bar over I del minus qa quantity squared, and we just showed that this term is identical to this term with the addition or the multiplication of e to the I q lambda over h bar, so we can make that substitution directly. Then we have to replace phi prime, and we replace it with its equivalent, which is q phi minus q times d lambda dt psi. And so, right, from the left side, we had to take the derivative of psi, and then we have the derivative of that second term times psi, right, because it's e to the minus I q lambda over h bar. That's this derivative here. It gives us the cancellation of h bar. It gives us the cancellation of the I, and we get a q in partial with respect to time of lambda applied to psi. And so we can cancel the two exponentials, and we're left with this term, which is exactly the same as this term over here. It's q d lambda dt psi, and so they cancel. And now we're left with IH bar d psi dt equals 1 over 2m times this quantity h bar over I gradient or del minus qa quantity squared plus q phi all applied to psi. And we recover the original Schrödinger equation. So that shows us that the Schrödinger equation is invariant as long as you add a phase factor to the solution. And so we can show, therefore, that under gauge transformation, there's an invariance of the electric field, magnetic field, as well as the Schrödinger equation. Now, we've talked about these gauges, but we haven't really said anything specific about them. So Maxwell's equations in potential form are given as follows. This is from electrodynamics. Del squared V plus partial with respect to t of del dot A equals minus rho over epsilon naught. V is now what I was saying was phi before. And the second Maxwell's equation is del squared A minus mu naught epsilon naught times the second partial of A with respect to time minus del dot A times the quantity del dot, or applied to the quantity del dot A plus mu naught epsilon naught partial of the potential with respect to time is equal to minus mu naught times the current density J. The two most common gauges that are used to transform electromagnetic fields are those which simplify these equations. And so the idea of a gauge transformation is to make it easier to solve an electrodynamics problem. So one of the gauges is called the Coulomb gauge. The Coulomb gauge is one where the del dot A is equal to 0. Now, if del dot A is equal to 0, this term goes to 0, And the first equation becomes the Laplacian of the potential, the scalar potential is equal to minus rho over epsilon naught. Very simple. And the second equation simplifies also a little bit because you remove this term, it's gone. So now you just have del of mu naught epsilon naught partial v with respect to t. And so you've removed one term out of that as well. The second potential that is commonly used is the Lorentz gauge. The Lorentz gauge states that del dot A is equal to minus mu naught epsilon naught partial of v with respect to t. So if it's equal to exactly this, then this whole third term in the second equation goes away. And now you're left with something rather simple, which is the Laplacian of A is equal to mu naught epsilon minus mu naught epsilon naught. Second derivative of A with respect to time is equal to minus mu naught J. This one does not simplify under those circumstances, but that's okay, because it's already relatively more simple.